All right. Six point two. There's only one more section in chapter 663, which we'll finish on Thursday. And then we'll begin breaking ground with chapter 7. All right. Section 6.2 is entitled Ratios, Proportions, and Variations. Some of these constructs you may have worked with in the past. And if so, that's just more power to you. It's just going to be review. But if not, you're in for a treat. All right. Ladies and gentlemen, we've all seen proportions before. Because if you've seen a fraction, you've seen a proportion. Excuse me, you've seen a ratio before. So by the time we get done with this section, we will hopefully understand how to write ratios in fractional form, solve proportions, use proportions to solve word problems that pertain to the real world, solve word problems that pertain to direct variation and inverse variations. A ratio. A ratio is nothing more than a fraction. And ratios can be expressed as a fraction, A over B. Or you could say the ratio of A to B. Or you can put a colon in between A and B. Okay, all these are equivalent ways of representing the ratio A to B. All right, now the thing with ratios is that the units in the numerator and the denominator are the same. In other words, we're talking about like feet to feet, or inches to inches, or pounds to pounds, or gallons to gallons. Okay, and because the units and ratios are the same, the units will cancel out, and therefore ratios are actually unitless fractions.
This one last week.
What's that?
Said I think we went over 6.2 last week, didn't we? I have the notes in my
Yeah, on Thursday I thought we did too.
yeah. I have my notes that I'm looking at.
Hold on, let me check the schedule here. Today is the 20th day of February, correct?
Yes. But after we got through discussing that last chapter 5 last week, we went into 6.2.
Okay, we were scheduled to do 6.2 today. Today is February 20th, according to the schedule. All right, well, and then 6.3 is actually slated for Thursday. So I don't want to really get too far ahead. Now, what we can do in 6.2 is actually look at more applications involving proportions and variations. And so this will
That'll work, yeah.
give us an opportunity to look at more word problems, which is always something that we could, stand to address and shore up in our thinking, because word problems always are challenging. All right. So we've already talked about ratios. Well, that is great. That just gives us a little bit more playtime here, which is awesome. All right, so we know ratios. Now proportions. We've already went over proportions. Do you remember? Proportions are equivalences between ratios. And to tell if a proportion is a valid proportion, you would look at the cross products, correct? Tell you what, for classwork 1, just to bring our minds back where they need to be, let's see if we can just verify whether these proportions are valid proportions or not. And the quickest, easiest, most efficient way to do that is to look at the cross products and see if the cross products are equivalent. All right, if they are, you have a valid proportion. If they are not, you do not have a valid proportion. So let's see if we can do that. Classwork 1. This is a good place to at least bring our minds back to where they need to be.
Okay.
So all we have to do to verify whether these are valid proportions is just look at the cross products. For instance, number one, if you take 3 times 15, you want to see if that product is equal to 5 times 9. And 3 times 15 is 45, and 5 times 9 is also 45. So that you can see that the cross products for the first wannabe valid proportion is 45, and so that is indeed a valid proportion. Okay. Another way to determine we have a valid proportion is to ask yourself, can 9/15 be reduced back down to 3/5? And by 3, it can be. So that is obviously a valid proportion. How about B? Is that a valid proportion? Looking at the cross products, 5 times 2 is 10. Is 5 times 2, which is 10, equal to 3 times 7? 3 times 7 being 21. The answer is no. So the cross products are not equivalent to each other here. 5 times 2 does not equal 3 times 7, so that is not a valid proportion. And so the only thing that would make this statement true is to put a slash through the equal sign. Okay. Number C, 14 times 8, which is going to give you 112, I believe. Is that equal to 7 times 16? 7 times 16 is also 112. So yes, this is a valid proportion. So the first and the last are valid proportions. The middle one is not. Any questions about verifying whether we have valid proportions or not? All you gotta do is look at the cross products. Okay. Then we got into solving proportions. To solve proportions, obviously at least one of our quantities must be unknown. And we can see that we have a variable x here in the denominator of the ratio on the right side of this proportion. To solve for x, we would cross multiply and equate the cross products. So when we cross multiply, we're going to have 12 times x, which is 12x, and that's going to be equal to 48 times 3. So we're going to have 48 times 3. Then we're going to, in order to solve for x, we will divide both sides of our equation by 12. X, therefore, is equal to, now 12 divides into itself once, divides into 48 4 times. 4 times 3 is 12. So x is equal to 12, and that proportion has been solved. Okay. This is just illustrating the solution process here. And when you get done, you can obviously check your answer. 12/48 is equal to 3/12. That is a valid proportion for several reasons. Number one, 12 times 12 is equal to 3 times 48. Another reason is that both 12/48 and 3/12 reduce down to the same fraction, namely 1/4. So they're obviously equivalent, and that's why in order to be a valid proportion, x must be equal to 12. Any questions about solving that proportion there? This proportion is a lot more difficult to solve, but nonetheless, it can be. we have x minus 5 over 10 is equal to x plus 2 over 20. And it is going to be our task to solve this proportion for x. Okay. Now to solve for x, we're going to cross multiply and equate the cross product. So 20 times x minus 5. We will set equal to 10 times x plus 2. And it's extremely important to enclose these variable expressions inside parentheses. Otherwise, you'll get a logical error. We can distribute here 20 times x is 20x. Minus 20 times 5 is 100. Using our distribution property on the right side of our equation, 10 times x is 10x. Plus 10 multiplied by 2 is 20. And now this is a linear equation that we have to solve for x. To do so, we need to get x on one side of our equation, eventually all by itself. And our answer then would be on the opposite side of the equation. Now, I prefer to bring my variable terms over to the left side of my equation. That's my preference. So to move a positive 10x, it's understood it's a positive 10x over to the left side to join the 20x, I'm going to have to subtract 10x from both sides because subtraction is the inverse of addition. That step is illustrating that I'm subtracting 10x from both sides of my equation. Now 20x minus 10x is 10x. Still got the minus 100. Equal sign. The 10x's drop out to 0 on the right side of the equation, or they cancel out, leaving you with 20. Now that we have a variable term on the left side of the equation, we need to continue to separate in bringing this constant over to the right side to join the 20. How do we legally, algebraically do that? Well, what's the inverse of subtraction? That would be addition. So we will add 100 to both sides of our equation. Now the 100s dive out to 0 on the left side of the equation. Negative 100 plus 100 is 0, or we say the hundreds cancel out, leaving you with your 10x equals 20 plus 100 on the right is 120. Finally, to get x all by itself, we need to get rid of this 10 that's being multiplied by x. And the inverse operation of multiplication is division. So we divide both sides of our equation by 10. $10x divided by 10 reduces down to 1x, or just x. 120 divided by 10 is 12. And ladies and gentlemen, we have our solution. X must be equal to 12. Again, it just so happens we get 12 again for our solution. All right, any questions about how we solve that proportion for the variable x? And, if you have time, you can always check your answer. If you put 12 back in here and here, it should check out. 12 minus 5 over 10. Is that equal to 12 plus 2 over 20? Is 7 over 10 equal to 14 over 20? You can look at the cross products now. 7 times 20. Is that equal to 10 times 14? And you bet it is. Therefore, we do have a valid proportion. So 12 is your solution to that proportion there. Any questions how we got that? Okay. The real beauty of mathematics is applying it to the real world. That's in my estimation. So let's see if we can apply it to this word problem here. A little bit of proportional reasoning while on spring break trip, a group of friends burns 12 gallons of gas in the first 228 miles, then stops to refuel. If they have 380 miles yet to drive and the SUV has a 21-gallon gas tank, can they make it without refueling again, assuming they fill up that gas tank totally full? Well, we know on 12 gallons, we got 228 miles. So we set up a proportion. 12 gallons is to 228 miles. As a 21-gallon tank is to 380 miles. Well, we can see if this is a valid proportion. So 12 gallons is a 228 miles. It has 21 gallons is 380 miles. All we gotta do is look at the cross product. So 12 times 380, is that equal to 228 times 21? Is that true or false? And we can use our calculator to help us out here. 12 times 380. Well, that gives us 4,560. And is that equal to 21 times 228? This is 4,788, correct? It's not a valid proportion. But one thing we could do here to get the miles per gallon here, the MPG, which we could take 228 miles. We can divide it by 12 gallons. This will give us the miles per gallon that our vehicle gets here. So let's do that. 228 divided by 12 is 19 miles per gallon. We know this better as MPG, miles per gallon. Now, we have 380 miles to go. All right, if we fill our gas tank up 21 gallons, are we gonna make it? Well, we get 19 miles per what, gallon, times 21 gallons. Notice when you multiply these together, the gallon units cross cancel out, leaving you with miles. So let's see how far we can go on a full tank of gas, 21 gallon tank of gas here. So 19 miles per hour times 21 gallons would afford us a distance of 399 miles. So it does look like, we should have enough gas, correct, to go 380 miles. All right. So it looks like we're going to be able to do it. Now, this is assuming, of course, that the driving conditions are going to be similar to the 228-mile driving conditions. In other words, if this remaining 380 miles is going to be totally up mountain sides, do you agree we might be what? We might be cutting it a little close. All right, so it just depends on what kind of driving conditions your last 380 miles is going to present to yourself here. But assuming that it's about the same driving conditions as before, yeah, you should have enough. All right. Okay. As part of a research project, biology class plans to estimate the number of fish living in a lake that is thought to be polluted. They catch a sample of 35 fish, they tag every one of them, and then release them back into the lake. A week later, they come back to the same lake and they catch 80 fish and find that of the 85 of them are tagged. About how many fish live in the lake? This is a useful way for biologists or park managers or ecologists to estimate the number of fish in a lake. Now, the key assumption with this lake, ladies and gentlemen, I must add these assumptions behind the scenes. The assumptions is that this lake is not fed by a river that leads to some other bigger lake, or in other words, this lake is self-contained. It's not, it doesn't have any other tributaries or rivers feeding into it or leading out of it. If that assumption is correct and we can adhere to that, then what I'm about to show you is pretty darn accurate. Okay? We can set up a proportion to estimate the number of fish in this entire lake. So the first time we went out in our boat, we caught 35 fish and we tagged and released them, correct? Okay, so we can set up a proportion here. 35 tagged fish is to X total fish in the lake. We come back a week later and we catch 80 fish. 80 total fish. And of the 80 total, how many are tagged? 5 are tagged. So we can set up a proportion. First time we went out, we caught 35 fish and tagged each of them and then released them in the back into the lake. Second time we came out, we caught 80 total fish, 5 of which were tagged. So we can set up a proportion. 35 tagged fish is to the total number of fish in the lake, as 5 tagged fish is to 80 fish we caught 1 week later. Now we solve this proportion for X. Cross multiplied. 35 times 80, and we set that equal to 5 times X. Divide both sides by 5. Now 5 divides into 35 7 times. 5 divides into itself once, divides into 35 7 times. 7 times 80 is 560. 5x over 5 reduces down to x. So we would project that there's about 560 fish in the lake. I'll tell you, you got to admit, this is a lot easier doing the problem this way than putting on some scuba gear and going down underneath the water there and trying to literally count all the fish in the lake. Do you agree? Which would be virtually impossible because the fish are not going to stand still for you. They're going to be moving all around. So good luck on that one. A lot easier to do it this way. About 560 fish in the lake. Now, the key assumption is that this lake does not have any rivers leading into it or out of it into some bigger body of water. That's the key assumption. Any questions how we did that problem? All right. Now, there are 2 different types of variations that we're going to touch base with. One called a direct variation, the other one's called an inverse variation. We say that a quantity y varies directly with x if there is some non-zero constant k such that y is equal to k times x. This constant is oftentimes called a constant of proportionality, or sometimes we call it a variation constant. And it has to be determined by using experimental data. Now, 2 quantities are often related in such a way that if x increases in value, what happens to y? If x goes up in value, y also what?
Goes up.
Goes up. And if x goes down in value, y's value also goes what? Down, correct? That's called a direct variation between 2 variables, x and y. And how much Y goes up or down, depending upon whether X goes up or down, is dependent upon this variation constant K. And again, to determine K, you'd have to have some data, okay? That's called a direct variation in the equation that looks like this. Y is equal to K times X. All right. Whoops. Okay. Here's an example. Suppose you earn $95 per day. Write a variation equation that describes total pay in terms of days worked. Use it to find your total pay if you work 6 days or if you work 15 days. So I will let P represent pay. That's going to represent the pay. And I'm going to let D represent the what? Number of what? Days worked, correct? All right. Number of days worked. Well, and then we can set up a variation, a direct variation. Pay is directly proportional to the number of days you work. So P is equal to K times D. Okay, there's your direct variation. Now to find K, we need some information. Well, wait a minute. What is K? They basically just hand it to us in this problem. K is a rate. So what rate hangs out in this problem? It's got to be a rate, something per something. What's my rate? There's K, $95 per day. So the total pay I receive is going to be equal to K, which is $95 per day times the number of days. Now we can answer these questions. If I work 6 days, what will be my total pay? You got to substitute 6 in place of the variable D here. So $95 per day times 6 days is going to give me what, 570 bucks of pay. Is this making sense here? Okay. That's a direct variation. Increase the number of days worked, increase your pay. Decrease the number of days worked, decrease your pay. They used Y and X instead of P and D. In reality, it doesn't matter what you call the variables, okay? All right, I think we will touch base with this one. When utility companies are strung above the ground, utility cables rather, the weight is important consideration. The weight of a certain type of cable varies directly with its length. They're going to let Y be the weight of the cable, X be the length of the cable in feet. The weight is in pounds. K is a constant, so we have a direct variation that exists between weight and length of this cable. They want you to find K and determine the weight of a 75-foot long cable. So we have a direct variation. To find K, we're going to use the fact that 20 feet of cable weighs 4 pounds. That's data we're going to use to find K. So in for Y goes 4 pounds of weight. In for X goes 20 feet of length of this cable. So we have 4 is equal to 20 times K. Divide both sides of this equation by 20. And 4 over 20, 4 divided by 20 is a decimal 0.2. Or you could reduce 4 over 20 down to 1/5. It's up to you. So K is equal to 0.2 pounds per foot or 1/5 pounds per foot. Therefore, our direct variation takes on the more precise look of Y is equal to 0.2 times X. Now they want to know in this problem, they want to know what the weight would be for a 75-foot piece of cable. So to answer that question, we just replace X with 75. So Y is equal to 0.2 times 75, or Y is equal to 15 pounds. So a 75-foot cable weighs 15 pounds. Any questions on how we did that problem? Okay. Inverse variation. We say a quantity y is inversely related to x if there is some non-zero constant k, so that the equation looks like this: y is equal to k over x. We would say there's an inverse variation between x and y. And again, k is that constant proportionality. What goes on here is if x increases in value, y's value decreases. If x's value decreases, y's value increases. We call this an inverse variation. Okay. Can somebody give me an example of an inverse variation between two variables in the real world? Any example? Anybody? Well, I can give you an example. All right, here's an example of an inverse variation in the real world. This is just one among an infinite number of examples that exist. If the weight of a vehicle you drive increases, then the fuel economy of that vehicle decreases. So if you drive a heavier vehicle, you're going to get lower fuel economy. You drive a lighter vehicle, you're going to get greater fuel economy. That's an inverse variation that exists between weight of a vehicle and its miles per gallon. That's one example. All right. Can anybody think of another example for us now in light of that example? An inverse variation. Any sort of inverse variation in the real world that exists between two variables. There's another good one. If the amount of sleep you get increases, then in general, the amount of doctor bills you have to pay decreases, and vice versa. That's an inverse variation. Another example. All righty. All right. Here's another example of an inverse variation. If the altitude above ground increases, the atmospheric pressure decreases, and vice versa. So altitude above ground and atmospheric pressure are inversely proportional to one another. Those are examples of inverse variations. All right. I don't like that example. Let's see. Here's a good one. In construction, the strength of a support beam varies inversely with the cube of its length. If a 12-foot beam can support 1,800 pounds, How many pounds can a 15-foot beam support? Suppose, ladies and gentlemen, this is a building here, and you got a beam jetting off the roof of the building that is this long here. And you put some sort of a weight out here. W for weight. Here's another building. And this is the length of a beam here. And you put another weight out here. Assuming that both these, so these are the buildings here. I have a question for you, ladies and gentlemen. The length of the first beam on the left is greater than the length of the beam on the right. Assuming that both these beams are made out of the same material, I have a question for you here. Which beam could support more weight? Beam number 1 or beam number 2? Again, assuming that the beams are made out of the same material. Anybody? Which beam could support more weight? Before snapping.
The last one?
What's that? You think beam number 1?
Yeah.
Okay. Well, does anybody beg to differ? Let me ask you this. Beam number 1 is longer than beam number 2. Do you agree? A lot longer. Which one's going to flex first under weight? Beam number 1 or beam number 2? Which one's going to start to bend under the weight? The first one, because it's a longer beam. You are correct. This first one's going to start to bend, ladies and gentlemen, under the load of the weight. This second one's going to be more rigid because it's shorter. I'll bet dollars to donuts the beam that gives out probably the first here, assuming they're both made out of the same material, would be beam number 1 because it's longer. Okay. The weight exerts more of what we say a moment on this beam here. There's not as much as a more moment or torque that's being exerted on the beam to the right because it's a shorter beam. Everybody see that there? Okay. Well, let's dig into this problem here. First of all, what we have to do is we have to write the equation that embodies this relationship between the strength of a beam and its length. Okay. We could let y maybe represent the what? The strength of the beam. And let x be equal to the length of the beam. All right, now it says the strength y of a support beam varies inversely with the cube of its length L. So y is equal to k over the cube of x, which is the length. How do you write the cube of x? You write it as x raised to the 3rd power. And there you go, ladies and gentlemen. That would be the equation that models this situation of the strength of a beam varying inversely as the cube of its length. Now, how can we find K? We can find K if we just have some data. And what data can we use? We can use this data. If we have a 12-foot long beam, it can support 1,800 pounds. So to find K, we're going to replace Y with 1,800 pounds. The length X is going to be replaced with 12 feet. Therefore, we can solve for K now. K is gonna be equal to 12 to the third power times 1800. Okay, get on your calculator and dial that up. What is 12 cubed times 1800?
Three, 1, 1, 0, 4, 0, 0.
Yeah, you get a big old number, don't you? So is that 3,110,400?
Yeah.
3,110,400. Now we can answer this question. How many pounds can a 15-foot beam support? Well, Y is equal to 3110400. And that's gonna be over what? 15 cubed. Get on your calculator and then we can find how much weight this beam can support. We're gonna divide that by 15 cubed. And I'm coming up with
1.6.
921.6 pounds, correct? That's how much weight this beam can handle before it snaps. Okay? Everybody see that there?
How do you get the 12 square? I mean the x squared 3.
How did I get the what now? Oh, x cubed?
Yeah.
Because it says the strength of the support beam Y varies inversely with the cube of its length. The cube of its length. What's the cube of x? Because x is the length. The cube of the length is x cubed.
I don't get it. Maybe I don't know. Maybe I'm missing
The
something.
strength of the support beam Y varies inversely. Now, when you say inversely, it's got to be Y is equal to K over X, correct? Not Y is equal to K times X, right?
Okay.
Varies inversely with the, now what does it say now? It says the cube of its length. What are we calling the length?
Cubed to the third power. That's what cube
Yeah,
means.
yeah. When you cube a number, that means you raise the number to the third power. So the cube of the length X is to say X raised to the what? Third power.
Okay. Okay.
In other words, if I cube 2, what does it mean to cube 2? It's going to be 2 raised to the what? Third power, which is 2 times 2 times 2, correct? If I cube 5, it means 5 raised to the what? Third power, okay? That's what cube means. Does that make any sense now? Why we're cubing X? Because it says the cube of its length X. All right. All righty, there you go. There's a solution. We just worked it all out. Okay, well, let's see if we can go to our textbook and have a little bit of fun here. So these problems here, we'll start pulling them out of section 6.2 here, if we can. Wow. Oh, here we go. Okay. And as always, feel free to look down through the section. They also give you some other examples that are worthwhile looking at. And I either have or will post a PowerPoint presentation on this section here. Okay. All right, so just for a little bit of classwork here, let's see if you can do this one that says try this one. Let's see if we can solve this proportion for X. Go ahead, we'll call that classwork number 2. So classwork 2. All right, solve this proportion for X. Go ahead and do that. Let's take a look at this problem here. Want to solve for X, so we cross multiply. So X times 25 is 25X. We set that equal to 7 times 22. And then we're going to need to divide both sides of our equation by 25. These reduce down to 1, and we're left with X, 1X or X. 7 times 22 is going to be 152. 125. And, I can't think of anything that reduces this down, so we could just leave it like that. Anybody get something like that?
Shouldn't it be 154 or no?
Yeah, I have 154.
Yeah, 154. All right, 154 over 20, 7 times 22. Okay, there's my Monday glitch. So, but this can still not be reduced down. So, I think that's it, correct? Now, you could turn it into a mixed number if you want to, but you don't have to.
I don't have the 25 at all, just 154.
Well, 25 times X is 25X. That's equal to 7 times 22. 7 times 22 is 154, but then you're gonna have to divide both sides of the equation by 25 though. You
Yeah,
actually,
and it
so,
gives you 6.16, and then you put 6.16 over 7 and do the other side with 22 over 25, and it comes out to 154. Both equal.
well, did you divide both sides by 25?
Yeah, I did.
So you have 7 times 22 over 25, correct?
No, I have 22 times 7. And then I've got 154. When you do 22 times 7, that give you
Yeah,
154.
and 154 over what, 25 though, correct?
25, right. And I got 25x over 25. You don't do them both and cancel out the 25, and that'll leave you with the x with
Yeah,
154.
yeah, these reduce down to 1, so you're left with X, just one X.
Right.
Right?
And then 154 over 25.
That's your answer. You can leave it like that, or if you want to turn it into a mixed number,
I divided it. I want 154 divided by 25. Give me 6.16.
yeah,
And then you can do 6.16 over 7. And then equal 22 over 25.
mhm. Yeah, you could do that.
And then I give you 154.
Yeah, 6 and 4/25. You turn that into a mixed number.
No, I didn't turn into a mixed number on my calculator. It just give us 6.16.
6.16, right?
Yeah. Uh-huh.
Okay. Well, we got the 6 here, correct?
Right.
And no, I got a fraction. What does that 4 over 25 give you there?
I don't have 4 over 25.
You got
It's just-
0.16. Yeah, this is the same thing as 6.16.
Yeah.
So 4/25 gives you the 1600ths part, okay?
Right. And then put that over to 7, because it's x over 7. You're trying to figure out what that x is over 7.
Yeah, yeah, I mean, but we found what X is, correct? It has to be this, right? 6.16. We've solved the proportion for X. If you wanted to check your answer, you'd put 6.16 over here, correct? And then verify that you have a true proportion, but
Yeah.
you don't have to check your answer if you don't want to. We found X to be this, okay? All right. Okay. All right, so moving on now. Now, would you know how to do this one here? Solve for X. See if you can do this one, solve this one for X. We'll call this classwork 3, I think. Solve this proportion for X. Okay, this will give us good practice in solving an equation. Okay, to solve for x, we're gonna have to cross multiply and equate the cross product, so 5 times this quantity, x plus 6, make sure you put it inside parentheses. Has to be equal to 15 times x minus 2. So again, we are cross multiplying and equating the cross products. And now we just have this equation to solve for x. Distributing the 5 times x is 5x, plus 5 multiplied by 6 is 30. And that's equal to 15 times x, which is 15x. 15 times a negative 2 is a minus 30. So that's how you distribute. Now it's time to separate the variable terms on one side of the equation versus constants on the opposite side. I'm going to bring a plus 15x over to the left side by subtracting 15x from both sides. 5x minus 15x is negative 10x, plus the 30 equals the 15x's drop out on the right side of the equation to 0, leaves you with minus a negative 30. Continuing to separate, now we want to move this 30 over to the right side of the equation. Since it's preceded by a plus, we need to subtract 30 from both sides to do so. Negative 10x. The 30s drop out on the left side of the equation to 0. And the right side, negative 30 minus 30, add up to negative 60. Finally, to get x by itself, we divide both sides of our equation by negative 10. Therefore, this implies that when we do that, this reduces down to 1x or x, and x is equal to a negative 60 divided by a negative 10 is going to be a positive 6, and we are done. Solution is x equals 6. Did anybody get that?
Yes, I did.
All right, positive 6 should be the solution. We have just solved that proportion. Okay. There we go. All right. Okay, let's get into some variations now. Let's go on down into the homework problems down here. All right. Number 30, ladies and gentlemen, I want you to do this problem right now for classwork. It involves setting up a proportion to answer the word problem. Number 30. We'll call it classwork. I think we're up to 4 now. Classwork 4. Go ahead. Problem number 30. Set up a proportion and answer that word problem. All right, so we're gonna set up a proportion to answer this question here. Out of 100 total milk drinkers, 57 prefer skim milk. They want to know at that rate, if we order 25 gallons of milk, how many of it should be skim milk? We set up a proportion. So out of 100 people that drink milk, 57 prefer skim milk. That's gonna be this ratio, as we don't know how many prefer skim milk if we buy, or how many gallons should be set aside for skim milk if we buy 25 gallons total of milk. We need to find out how many gallons of this 25 gallons must be skim milk. So we solve for X now. So we cross multiply. So 57 times 25, and we set that equal to 100 times X. And now we just solve for X. Divide both sides of our equation by 100. And X is equal to 57 times 25 divided by 100. Now, when you bring that up, you know, you can dial it up on your calculator. And you come up with X being equal to 14.25 gallons should be skim milk. You got your answer. 0.25 is 1/4 or 1/4. So you could also think of this as being 14 1/4 gallons is to be skim milk. Did anybody get that?
$14.25, yes.
All right, nice job. You are doing proportional reasoning. We do proportional reasoning all the time in our lives. We just don't realize that we're doing it. All right, try number 36. We'll call this, we'll call it classwork. I don't know, what is it, 5 or whatever. If I lose track, don't worry about it. It's called a classwork. I still would like to have it. So we'll call this a classwork number 36. See if you can answer that question using proportional reasoning. Okay, so we can set up a proportion here and answer this word problem here. In 8 months, we put 6,600 miles on this vehicle. In 2 years, which is 24 months. Let's find out how many miles we expect to put on this vehicle, assuming we continue to drive at this rate. That's the key assumption in this problem. Cross multiplying 8 times x is 8x. And set that equal to 6,600 times 24. Divide both sides by 8. These reduce down to 1, these 8s, so 1x is x. Look at this, 8 divides on itself once, divides on 24 3 times. And 3 times 6,600 is going to be 19,800 miles. Well, don't they continue to drive at this rate? Are they going to stay within their lease's requirement?
Yes.
The lease allows 10,000 miles per year, which is 20,000 miles over 2 years. Do you agree? So this is less than 20,000 allowed miles. So it looks like they'll be okay. All right. Anybody, we get that? Everybody?
Yes.
So we're good on that. All right. So it looks like we're gonna satisfy the lease. Suppose, assuming we don't drive any more than that, though, because this is pretty close. All right, let's move on now. Okay, let's see here. All right, number 48 is a direct variation. Let's see if you can do this for classwork. We'll call it classwork. We'll just call it classwork. I forgot. I ran out of numbers. All right, ladies, I want to see if we can do this. The number of tickets purchased for a prize varies directly. So the number of tickets varies directly with the amount of the prize. For a prize of $1,000, 250 tickets are purchased. Find the approximate number of tickets that will be purchased on a prize worth $5,000. I want you to set up a direct variation equation, solve for K, then answer the question. Number 48, classwork. we set our direct variation up like this. The number of tickets purchased is directly proportional to the prize value. And in order to find K, the variation constant, we need data. And the data says that if the prize is valued at $1,000, 250 tickets will be sold. So Y is 250, X is $1,000. And now we just solve for K. To solve for K, we divide both sides of the equation by 1,000. And therefore K walks out of this with a value of 1/4 or 0.25. Now we can answer the question. And the question is, now that we know our direct variation is Y equal to 0.25 times X, we can now answer the question. And the question was, how many tickets would be purchased if the prize value is worth $5,000? So now we just let X be 5,000, multiply it by 0.25, and you got your answer, the number of tickets purchased. And therefore, the number of tickets purchased is going to be, what? 5,000 divided by 4 is going to be 1, 2, 1250. Wait, 100.
Yeah, 1250.
1250. 1,250 tickets.
I did it differently and I got the same answer. I'm trying to make sure I'm following you.
Did you set up a proportion?
I did.
All right, that would work okay. Just be careful when it comes to variation problems versus proportions. Proportions are okay as long as we have a linear relationship between X and Y. If you don't have a linear relationship, like if this was X squared, then a proportion is not going to work, okay?
I got you.
You have to have a variation, so just be careful on that. All right, that's number 48.
How do you know like what you're gonna make like the price value and like the ticket? Like, could you made the tickets X and the price value Y, or like how do you figure out that?
Well, because it says the number of tickets purchased for a prize varies directly with the amount of the prize. So the Y is on the left side of the equation, of the variation equation, and the number of tickets comes first before the prize value. So the number of tickets would be Y. That's always on the left side, and the right side would be the prize value right there. Okay, so it depends on how it reads here from left to right. Okay, does that help? Because
Yes, thank you.
the number of tickets comes first before the amount of prize, and the amount of prize comes after the words varies directly. Y would be the number of tickets purchased. X would be the amount of prize. Okay. All right, let's try another one here. Let's see. We already did that one there. All right, here's a beauty here. In karate, the force needed to break a board varies inversely with the length of the board. So the longer the board, the less force is required to break the board. The shorter the board, the more force is required to break the board. If it takes 5 pounds of force to break a board that is 3 feet long, how many pounds of force will it take to break a board that is 5 feet long? Notice this is an inverse variation here, okay? So see if you can set up an equation, ladies and gentlemen, involving an inverse variation. And let's see if we can use it to answer this word problem. We'll call it another class work here, number 55. All right, go ahead and try number If you're still hung up on this, you might wanna, this give you a little jump start, so maybe you wanna start developing your equation this way. Y will be the force needed to break the board, X will be the length of the board in feet. We have an inverse variation between force and length, so Y is equal to K over X. All right, now maybe that'll give you a jump start there. See if you can use that to propel yourself to answer this question.
I don't know if I did it right, but I think I got it.
All right, hold on and we'll check it.
Okay.
So, ladies and gentlemen, we found K by using the fact that 5 pounds of force is needed to break a 3-foot long board. Y takes on the value of 5, X takes on the value of 3. This is really a proportion. 5 over 1 equals K over 3. To solve for K, we cross multiply and equate to cross products. 3 times 5 is equal to 1 times K, or K is 15. Now we can answer the question. If we have a 5-foot long piece of board, how much force in pounds will be needed to break it? Replace X with 5. 15 divided by 5 is 3. 3 pounds of force will be necessary to break a 5-foot long piece of board. Anybody get that?
Yeah.
Okay. Working with variations a little bit. Now the next one's going to be really interesting. Number 56, the weight of a body varies inversely with the square of the distance from the center of the Earth. If the radius of the Earth is 4,000 miles, how much would a 150-pound woman weigh 500 miles above the surface of the Earth? Ladies and gentlemen, in physics or in our universe, there's a lot of inverse square laws. For instance, the intensity of light varies inversely with the square of the distance between the source of light and your eyeball. Okay, that's an inverse square law. Gravitational force is an inverse square law. That's what's going on here. So the weight of a body varies inversely with the square of the distance. All right. So to get started on this word problem here, we have an inverse variation. Suppose I let y be equal to the weight of a body, and this will be in pounds, and let x be equal to the distance from the, hold on a second here. Distance from the center of the Earth. Now, I must warn you, this is a picture of the Earth, not exactly drawn to scale, obviously. This is the radius of the Earth, which they tell us is 4,000 miles about. So it's about 4,000 miles to the center of the Earth. That's how big our planet is. So ladies and gentlemen, X is the distance from the center of the Earth. The distance from the center of the Earth is X. Now hold on a second here. Wait a minute here. Got to be careful here, because it's the distance between the center of the Earth and the body, not the distance between the body and the surface of the Earth. So, how are we going to do this problem here? Let's see. Well, what I should say here, instead of X, what I should say is X plus 4,000. Miles. X will be the distance above the Earth's surface, okay? So if this distance is X, then the total distance between the person above the surface of the Earth and the center of the Earth is then going to be what? X plus what? 4,000 miles, correct? Is that true? All right, anyways, we can set up our inverse variation. The weight of a body varies inversely as the square of the distance between the body and the center of the Earth. The square of this distance is going to be this right here. And so actually, this is a very difficult problem to solve. We haven't really solved one like this before. So I'm willing to walk us through this one. I don't think I'll give you one that's complicated, but anyway, might as well finish it. It says, how much would a 150-pound woman weigh 500 miles above the surface of the earth? Well, if a woman weighs 150 pounds on the surface of the earth, how far away is she from the center of the earth? If she's standing on the surface of the earth, she's 4,000 miles away from the center, correct? So we can use this data to find K. The woman weighs 150 pounds. If she is 4,000 miles away from the center of the earth, meaning she's on the surface of the earth, she's not above the earth's surface. So X would be 0 here, meaning she's 0 miles above the earth. We'd have to square this. So what we got is we got a proportion here. 150 over 1 is equal to K over 4,000 squared. This implies then that K is really going to be equal to 150 times 4,000 squared. So K is going to be, you know, kind of a big number here. So let's get on our calculator and see if we can dial this up here. So 150 gets multiplied by 4,000 squared, which is a big number. That's going to be 0.4 times 10 to the what power? 10 to the 9th power. Do you agree? Therefore, our inverse variation is y is going to be equal to 2.4 times 10 to the 9th power in scientific notation form over x plus 4,000 squared. Now we can answer the question, and the question is this. If a woman's body is transported to 500 miles above the surface of the earth, how heavy is she going to be? What's going to be her weight? Well, now we just let x be 500 miles. She's going to be 500 miles above the surface of the earth. So her weight is going to be 2.4 times 10 to the 9th power divided by 500 miles plus the radius of the earth is 4,000 miles squared. This is going to give us the weight of the woman in pounds. So 2.4 times 10 raised to the 9th power divided by 4,500 squared. Get on your calculator and see if you can dial this up. Make sure you can do that on your calculator, if nothing else. And just try to find out how heavy this woman's going to weigh if her body starts moving further and further away from the surface, from the center of the earth. The attraction of gravity would be less. And so therefore, I surmise her weight is going to start to decrease the further she moves away from the center of the earth. Let's see if we can do the calculation on a calculator.
What, 18.5?
Yeah, I'm getting approximately about 118.5 pounds. So, ladies and gentlemen, she will have lost how much weight?
Thirty-one and a half.
31.5 pounds lost. Hey, we just found another way to diet. All you got to do is just go farther above the Earth's surface and you'll lose weight. Isn't that cool? No diet necessary. On the moon, ladies and gentlemen, the acceleration of gravity on the moon is 1/6 of what it is on the Earth. And so your weight will be 1/6 on the moon as opposed to what you weigh on the Earth. In other words, if you weigh 180 pounds on the Earth, on the moon, you're going to weigh 180 divided by 6 or 30 pounds. That'll be your weight on the moon. 30 pounds on the moon. Talk about what? Losing weight quickly, huh? That's the way to lose weight. Just go live on the moon. All right, that was a little bit more complicated of a problem there, but nonetheless, I showed you how to handle that. Okay, that's called the inverse square law that gravitation obeys here on planet in our universe. It's an inverse square law. Right. All right. Let's see if there's anything else here. Now it is 2:14. Let's see. Yeah, here's another problem here. Maybe you could try this one later on. This will be the last classwork. The intensity of sound varies inversely as the square of the distance from the source. A sound with an intensity of 300 watts per square meter is heard from 20 feet away from the speaker. What is the intensity of this sound 50 feet away from the same speaker? Go ahead as an inverse variation. Set up the equation, solve for K, and use it to answer this word problem. We'll call this the last classwork. We'll call it a one for the road, classwork for the road. Go ahead and do that one. All right, here you go. It's an inverse square law, just like gravity is. This is the same law that sound intensity shares. To find K, 300 watts per square meter occurs when you're 20 feet away from the speakers. So you put 20 in for X, 300 in for Y, multiply both sides by 20 squared to solve for K. K therefore is like 120,000. Then they want to know what the intensity of the sound is going to be if you're 50 feet away from the same speakers. You let X be 50. And you go ahead and crank that out. And what is 120,000 divided by 2,500? It's going to be 48 watts per square meter. Okay, so you can see that the sound intensity drops off radically with distance. It doesn't drop off at a linear rate. It drops off with an inverse square rate. Okay. All right, anybody get that?
Yeah.
All right, ladies and gentlemen, that's it. I'm going to stay on the line for the next couple of minutes if you have any questions or comments. Otherwise, you have a great day. And we will begin to look at the XY Cartesian coordinate plane in 2 days. And we'll show ourselves how to plot points, how to graph linear equations, how to determine the slope of a line, how to write the equation of a line, and how to use slope-intercept form for a line to actually apply and model worldly application problems. So we'll touch base with that in 2 days in section 6.3 as we close the door on chapter 6. All right, have a good day.